Okay, in today's video we're going to be talking about equilibrium applications of Newton's laws of motion. So what is equilibrium? An object is in equilibrium if it has no acceleration. In other words, it's not moving or moving with a constant velocity. And in that case, all the forces in the x have to equal 0 and all the forces in the y have to equal 0. This is very similar to our vector addition lab we did at the beginning of the year. All the force in the x added to 0, all the force in the y added to 0 because the object wasn't moving. And remember, the object could be moving with a constant velocity and still be in equilibrium. Okay, so let's think about how we would solve these type of problems. The object or objects in which equilibrium are to be applied are selected. In other words, what is the object you're going to be looking at or objects you're going to be looking at? And then you draw a free body diagram for each of them. And you include obviously only the forces acting on the object, not forces the object puts on its environment. And you choose a convenient coordinate system and resolve all the vectors into their components, the x and y axes. And then you use Newton's laws and equations to solve for any unknown quantities. So it's pretty straightforward. So we're going to give it a shot with this problem here. Okay, so you got some guy's leg in traction. The tension, this is free to move, this is free to move, and this weight holding down is pulling on his leg, both T1 and T2. And what we're looking for is we would like to find out what the force in T1 is, the tension, excuse me, in T1 and T2 is, and also what this force here is. Okay, so we have the object, which is basically the center of this, and there's three forces acting on it. One pulling back this way, one pulling this way, and one pulling this way. So we're going to draw a free body diagram. Here's our free body diagram. We represented this center position just by a dot, and we have a force acting backwards, T1 pulling up into the right, and T2 pulling down into the right. And we broke this into x and y components. I found that the idea of thinking of it along the axis of F and calling that the x-axis would be the simplest. And then I created a y-axis perpendicular to that. So that allows me to break this tension into its components, its x and y components, as well as this tension into its x and y components. So we took this vector, we broke it into how much is in the x and how much is in the y. Okay, so if you're looking at this angle right here, this would be T1 cosine of the angle, and this would be T2 sine of the angle. Normally I like to draw it over here, but they drew it here for this demonstration. And we did the same thing down here. Alright, so now we have a free body diagram, and we've resolved it into components. Now we need to determine what all the forces in the y equal. Well, it's an equilibrium, so it has to equal 0. So we have T1 sine of 35 minus T2 sine of 35 equals 0. Now let's see where this came from. You have T1 sine of 35 acting upwards. There you go, it's acting upwards, pulling up. At the same time, this is pulling down. So that's why this one's positive and this one's negative. And in the x direction, it's still equal to 0 because it's not moving. And here we have T1 cosine of 35 pulling to the right and T2 cosine of 35 pulling to the right with F pulling to the left, so it's negative. And we try to solve for unknowns. So we take our first equation and realize that sine of 35 and sine of 35 are in all terms, so we can get rid of that. And we determine that T1 minus T2 equals 0. And we know that T2 has to equal the weight that's hanging down on it, causing this tension, right? So T2 is just equal to 2 kilograms times 9.8 or 21.6 newtons. So that means that T1 is equal to T2, which is equal to 21.6 newtons. Now to find out what's happening with F, we have to use the X equation because F is only in the X equation. All right? And once again, we could divide both sides by, well, we can't actually divide by 35, can we? Because there's this term F doesn't have a 35, a cosine of 35 in it. But we do know that T1 and T2 are equal to each other. And why are they equal to each other? Because these two angles are equal. And not all problems will they be equal. You'll see that in the next problem we'll cover. So that we know that we could replace one of the T's with, we could replace T1 with T2 because basically they're the same thing. So 2T2 cosine of 35 equals F, or F is equal to 35.3 newtons. And that's a very simple application of equilibrium problems, static equilibrium problems. Let's look at something that's a little bit more complex. Okay, you got a guy trying to put an engine block into a car that's being held up by a pulley up here. And obviously this tension is probably taking most of the weight, I would think, just looking at it. And he's pulling it out to the right, trying to position it correctly. All right, so we have to draw our free body diagrams. T1 is acting that way, has a component in the y, T1 cosine of 10, and in the x, T1 sine of 10. Now, it's interesting to notice that a lot of people always think that the y direction will be sine and the x direction will be cosine, but it all depends on what angle they gave you. In this case, they gave us this angle. So the x is actually the x direction is actually sine, and the y direction is cosine. And we resolve this vector into its components as well. We have T2 sine of 80 and T2 cosine of 80. Now if you're having a difficulty understanding this, take a moment, pause the video, look at it, and determine where these vectors are coming from and where these components are coming from. And obviously we still have weight acting down. So we have T1, T2, both broken into components, and weight acting in the y. So we could summarize this. Okay? So T1 has an x and y component, T2 has an x and y component, and weight only has a y component. And by the way, that weight is 3,150 newtons. Okay, now let's see if we can come up with some equations for this. Okay, in the x direction, we have negative T1 sine of 10 degrees, because it's pulling to the left. Positive T2 sine of 80, because it's pulling to the right. All that must be equal to 0. And then we have in the y direction, we have our T1 cosine of 10 degrees, pulling up. Our negative T2 cosine of 80 pulling down. That's why it's pulling down, so it's negative. And weight is obviously negative. All right, so we actually have two equations and two unknowns. So we're going to have to solve them simultaneously. So the first equation, the one up here, I'm going to solve for T1. And T1 ends up equaling to this quantity here. Okay? If you need a moment to figure out how I did that, pause the video and look. Okay? And now I'm going to be able to take that equation and substitute into the second. So wherever there was a T1 in the second equation, I'm going to put all this stuff. Okay? So I took all this stuff and put it in for T1. Now I only have T2s and weight, which I know. Now I'm able to solve for T2. And when I do that, I end up with 582 newtons. And you can confirm that on your own as well. Okay, now that I have one of the tensions, I'm able to calculate the other tension. And I just have to go back now into the first equation, or any of the equations actually, and plug in what T2 is, and now I'm able to figure out what T1 is. Okay? And this is just algebra, so if you need a moment to look at it, once again, pause the video, see where I came up with these equations, how I manipulated the algebra to come up with an answer of 3,300 newtons. And that's basically how you do equilibrium problems using Newton's laws. Basically, to summarize it, what you're doing is you're picking the object you're looking at, you're drawing free body diagrams off it, you're breaking any vectors into the components, and then you're solving for any unknowns. And sometimes you have to solve simultaneous equations.